Modern cryptography relies on a specific mathematical bottleneck, integer factorization. Finding the prime factors of a massive semiprime is a strictly discrete mathematical problem, notoriously resistant to classical computational shortcuts. Traditional factoring relies on sequential trial division. A classical computer is forced into a brute force approach, dividing the target number by primes, one after another, until it finds a match. As the integer scales up, the time required to compute it grows exponentially. Quantum algorithms, specifically Shor's algorithm, offer theoretical shortcuts by evaluating multiple possibilities simultaneously. Classical physics, running on standard silicon hardware, has historically lacked an equivalent mechanism. The paper Numerische Crystallography und Resonanzbasierte Factorisierung proposes a different path, linking continuous physical simulations directly to discrete math. This process changes the geometry of the problem. It translates a discrete integer n into the spatial coordinates of a simulated crystal lattice. Once encoded, we can substitute sequential searching with simulated wave interference. We are essentially treating the number as a physical object. The simulation irradiates this numerical lattice with waves, attempting to isolate prime factors purely through physical resonance. Moving from discrete numbers to continuous space allows us to bypass computational brute force. The simulation forces the laws of wave mechanics to perform the calculation. The algorithm starts with a target integer n and an empty spatial matrix. First, the integer n scales the primary axes of a numerical unit cell, setting boundaries. We populate this cell with an atomic basis. These nodes, derived from n, form Bragg planes, parallel geometric constraints connecting nodes across the unit cell. This construct is entirely synthetic. There is no physical matter involved, only a numerical constraint matrix designed to mimic solid-state geometry. Because the mapping is deterministic, every unique integer n results in a completely unique lattice geometry. The abstract target number is now a physical terrain. We solve the problem by navigating this continuous space rather than performing millions of individual divisions. To model the way waves interact with this terrain, we must translate the physical lattice into reciprocal space. This transition uses a Fourier transform to map the distances between nodes into their spatial frequency equivalents. The physical Bragg planes are replaced by a frequency matrix representing potential periodic structures. We inject a continuous spectrum of simulated numerical wavefronts across this matrix. As these wavefronts strike the lattice points, the vast majority immediately cancel each other out. This occurs because constructive interference only survives if the wavelength matches the spacing between the encoded planes. If a frequency is not a factor, the reflections from different layers of the lattice are slightly offset. These misaligned peaks and troughs collide, systematically flattening the wave to zero. This physical interaction allows us to test thousands of potential divisors at the same time. The lattice acts as a physical sieve, instantaneously rejecting non-factors through wave cancellation rather than expending energy on sequential division. While most waves are neutralized, a few specific frequencies pass through the reciprocal lattice unchanged. At the resonance condition, a wave perfectly matches the lattice spacing, triggering a massive amplitude spike. This constructive interference only occurs at exact integer divisors of n. Locating this peak in reciprocal space reveals the original integer's prime factor. No division took place. The system simply listened for the loudest echo in the numerical crystal. The physical superposition of waves achieved what would normally require extensive, iterative processing power. We didn't find the factors by searching for them. We designed an environment where they were the only mathematical entities capable of surviving a physical wave collision. At scale, this technique could allow multiple semiprimes to be processed simultaneously within a single simulated environment. By weaponizing parallel wave superposition, we bypass the limitations of sequential trial division. This suggests a different class of computational complexity. Traditional division costs grow exponentially with the size of the number, but resonance-based factoring follows a different curve. There is a heavy initial computational overhead required to simulate the high-dimensional lattice and its basis functions. However, once the lattice is established, the actual sieve is nearly instantaneous. For massive integers, this creates a significant break-even point, where the simulation is faster than any classical search. This creates a new vulnerability in classical cryptography based purely on geometric modeling. This framework allows classical hardware to access the benefits of parallel evaluation by simply changing the operational environment. The line between abstract number theory and physical modeling is thin. By changing the geometry of a problem, we alter the tools available to solve it.